Well, welcome everyone to our weekly Warnell Seminar. Just a reminder, my weekly reminder, I'll never forget, but some students do sign up. Please sign up. If you don't sign up, you're not in the class for me. For those online, write me an email. I yell at that because sometimes people are like, I didn't realize I had to be there or let you know. So please either sign up or let me know via an email. Otherwise, for me, you're not in class. I've seen you, but you're not in class. All right, with that, we'll have Dr. Markovitz introducing our speaker for today. So Dan, I'll leave it to you here.
Dr. Markovitz is just happy you're here, whether you're in class or not. Thanks for being here. Hey, it's my pleasure to introduce Dr. Mukesh Kumar. Hey, will you tell me about the cricket player from India whose name is Mukesh Kumar? Is he very famous, or he just comes up when I Google your name?
Well, I am not aware of him, so.
All right. Let me tell you a little bit about Dr. Kumar, who did his bachelor's in India in civil and environmental engineering at the Indian Institute of Technology, and then came to the US where he did his PhD at Penn State. That's where my awareness of him begins, because he worked on a spatial hydrologic model, which is called the Penn State Integrated Hydrologic Model, PIMS, is how I knew it. And then we actually got most acquainted. We got a grant, a critical zone observatory grant, while I was here. And Dr. Kumar was at Duke, and Duke was the lead institution, but we had 4 faculty at UGA that were on that grant. So we started working together a lot more closely at that time. After he did his work at Penn State, he was in California for a short time in Santa Barbara, but then really was on faculty at Duke for not quite a decade, maybe 7 or 8 years. And then most recently ended up moving to the University of Alabama, where he is also in their civil and engineering department there. And in 2024, I was just making fun of Dr. Kumar, the University of Alabama College of Engineering gave him a Rising Faculty Star in Research Excellence and Innovation Award. So he's obviously been knocking it out of the park there at Alabama. Continues to work in a lot of hydrologic stuff. I think today he'll show you a little bit that he's decided trees are an important part of the hydrologic model. That was not true early in his career, with a lot about water flow and groundwater and soil moisture. So has been working with a growing hydrologic contingent there at the University of Alabama. Pretty well-funded guy, had an NSF Career Award while he was at Duke, and was telling me about all the money he has now through the Department of Energy and National Science Foundation. So welcome. Please tell us a little bit about what's going on in your world. Thanks.
Sure. Thanks a lot, Dan, and thank you everyone for being here. It has been a great visit till now. I'm in forestry school, so I'll not try to make a case that trees are important. And of course, that was a bit of realization maybe 7-8 years back, why we need to study them and study them carefully. But perhaps in today's talk, what I'll do is I'll try to highlight our attempts at decoding maybe tree functions, the stresses they experience and mortality that may experience, and what are the challenges in estimation. So let me jump right in. I mean, certainly I do not need to highlight how important evapotranspiration is. We can see this result from the landmark Oti and Kane paper, where they estimated that around 59% of the terrestrial precipitation gets lost because of ET. Now, let's see. I mean, in addition to its influences on the water budget, certainly it's influencing all other connected processes, whether it's a stream flow, groundwater recharge, soil moisture, so on and so forth. And so the natural question to ask is, haven't we figured out ET yet? It's already in our textbook. There are equations in our textbook, use Penman-Monteith equation and so on and so forth. But how good are we with predicting the ET? I mean, one would wonder. I mean, haven't we figured this out yet? And And if you look at the current model results, actually, so here are the results from CMIP6 models. And look at the extent of variations in ET estimate, terrestrial ET estimate, and then ranges from as low as around 380 millimeters to as high as 800 millimeters over the terrestrial, over the terrestrial land surface. If you look at Oki and Kane's estimate, the annual average evapotranspiration is around 490 millimeters. Over oceans, that's around 1180 millimeters or so. So overall, for the Earth, it's around 970 millimeters. And not only the annual estimates are different across the models, but even when we look at the spatial estimates from land surface model, machine learning model, remote sensing, you can see a significant degree of variation or discrepancies between this. So what is happening? Now, this could be because of the transpiration estimates that are being used in these models. And if you look at, so here I'm showing, a snapshot of some of the papers that identify how much fraction of ET is the transpiration. And there also, there is a significant degree of disagreement. In fact, some older papers had estimates from 44% I should say, because they modified the model in there. From 44% to this based on isotopic data by Jessica and et al. From 80 to 90%. So there is a significant degree of disagreement in the estimates of how much of ET is from transpiration. Okay, so uncertainty can be from various sources. Now, one of the challenges in at least modeling transpiration is we need to know the stomatal kinetic, which is how much of the stomata opens up and allows the moisture to escape away from the trees or from the leaves into the atmosphere. So how is this generally being modeled? So there are these empirical models that model stomatal kinetics, or just that how the stomata opens and closes during the day. And these models, what they do is they account for radiation, temperature, vapor pressure deficit, soil moisture. And they use these independent functions of all of these properties to obtain a stomatal conductance term. So that's how they end up calculating. And some examples of these models, I mean, if you do not recognize it, you must have seen in some other forms. For example, Jarvis formation. All it is doing is exactly this, just that these functions that are being used in these models may vary. The same can be said for Balbury and Luning formulations also. So all of these are empirical formulations that try to evaluate stomatal conductance. But irrespective of these formulations, what we can notice is in these formulations, we are always using these independent functions of moisture, VPD, light, and temperature, right? But in reality, these variables are not affecting independently. They are connected inextricably, and so recognizing this from tree physiology literature, over time, then ecohydrologists also started developing what they call is a plant hydraulic based model, where what they are doing is, well, in some ways you can say it's similar, but here G star is not just dependent on the moisture, but it's also dependent on VPD. And similarly, the sensitivity of VPD M is time varying and dependent on moisture and VPD as well. And what plant hydraulics model do is they try to connect they try to model the transfer of the moisture from the root zone through the xylem based on some kind of, let's say, cohesion tension theory representation. Then it gets to the atmosphere, gets to the leaves first, gets to the leaves depending on the turgor pressure in the leaf, which is determined by how much moisture is in the leaf. That ends up determining the stomatal kinetics, and then that determines how much of the water is lost from the leaves to the atmosphere. So here, again, as I said, vapor pressure deficit, soil moisture, that is affecting the leaf water potential, and then that ends up affecting soil And this has kind of become, so to say, state of the art in the eco-hydrological literature and is being incorporated in, current generation or the next generation models that are being developed, be it by DOE or NCAR, in any of these models, plant hydraulic model is being estimated. Now, how much of the gain do we get from plant hydraulics model? Let's look into that. If we look at, so this is the result from between 50 to 60 sites, if I recall it, maybe 56 sites or so. So here we are showing on the left, I'm showing you the R square estimate of ET with respect to the observations at eddy covariance site. On the y-axis is the empirical model, and on the x-axis is the hydraulic model. So certainly you can see there are more number of hydraulic models below the 1-to-1 line, indicating that there is some improvement in the hydraulic model, but not as much. I mean, generally they are falling on 1-to-1 line. So there is marginal improvement in the total ET estimation based on the plant hydraulic model, but the improvement is not significant. However, if we just focus on the period when the plant is really stressed, and by that I mean when there is not enough soil moisture or the vapor pressure deficit is high, which means that more the atmosphere or moisture deficit in the atmosphere is high. At those periods, if you look during those periods, now we can see that here, let's say high vapor pressure deficit period, low soil moisture periods. In these periods, certainly the hydraulic model outperforms the empirical model. And so that's quite important. What this is showing is, yes, plant hydraulic model improves our estimate of ET during stress periods, right? And that's important, especially if our interest is in tracking plant stress, whether it's crop stress or tree stress, or eventually predicting tree mortality or so. Now, if we, however, so why that is happening, let's say, so this can be looked at from a perspective of how these models are behaving in response to stress. So on the y-axis here, I'm showing you how much is the restriction in ET because of how much is the restriction in ET because of stress in an empirical model, and how much is the restriction in ET because of stress in the hydraulic model. So x-axis is for hydraulic model, y is for empirical model. And the triangles are representing the restriction in ET because of VPD only. And circles are representing restriction in ET because of soil moisture. So what we find out is that the restriction of ET because of soil moisture in empirical models is much higher, which means that if there is smaller soil moisture, then the empirical models will predict much lower evapotranspiration than a plant hydraulic model. Okay. So it has much more restriction. Now, what is its implication, which I'll show later on as well, but let's say because of climate warming, VPD is increasing, vapor pressure deficit is increasing because of climate warming. And so in this case, what will happen is, as you can see with these triangles, here we are finding out that the restriction of ET because of the VPD is much higher in hydraulic model. So the hydraulic model will show a much smaller ET than an empirical model, right? So with the changing climate, essentially what this is showing is that the ET being predicted by the empirical model is generally smaller. The ET that is getting predicted is generally higher than what a plant hydraulic model does. So in other words, if we assume for a moment that plant hydraulics model are more accurate, then with climate warming, when the vapor pressure deficit is high, what we are saying is that empirical model will show a higher ET. Okay, so it is over predicting ET. And so in some ways we can think of it as a good news that current models are maybe predicting more ET in future than it should be, which means actually the ET should have been less or should be less, which means there will be more water available in surface water system. But on the other hand, if one has to predict the stress, what it means is they are over predicting the stress in the plants, right? It is also to be noted that if you look at the crop model, most of the crop models, be it even DSAT, I mean, it came in our discussion today, all of these models are still based on empirical, right? So the estimates from these models regarding crop stress and then consequently productivity, it's going to directly impact those estimates, right? And these differences that we see between these models are just because how the functions are getting represented. As I noted earlier, in empirical model, we are using independent functions for reduction in this conductance because of moisture. On the other hand, in plant hydraulic model, it's dependent on leaf water potential, which is dependent both on the moisture and vapor pressure depth. And that's what, and in this case, that's why M is also dynamic. So the values become different and I, I'll not get into too much of detail, but unless there are questions in this regard. But overall, what we find out is because of the differences in how we are representing the response of moisture and VPD on stomatal conductance, that plays a big role in determining how much of the stress a plant will feel, and especially in our predictions under a changing climate, when the warming happens. Okay, so this kind of highlights that, well, there is a need to maybe improve the current generation empirical models. There is a need to improve stomatal kinetics. But still, that does not tell us, is our plant hydraulic model still the best we can do? Are there errors in the plant hydraulic model itself? And is there a need to improve it further? And so there have been a lot of papers which have tried to compare, let's say, okay, so I'll just skip. So that have tried to compare plant hydraulic model and empirical models. And they have come to similar conclusion that plant hydraulic models are better at capturing the stresses, especially when the soil moisture is low or the VPD is high. But still we don't know the structural constraints that exist in plant hydraulics model. So to answer that, what we did was we looked at around 84 FluxNet sites where eddy covariance data of ET are available. And that covered around 10 land covers over 642 years of data. And for this data set, what we did was we implemented both empirical and plant hydraulic model. Okay. We calibrated them exhaustively, which means that there cannot be error in these models because of parameters. Okay. If there are errors, that can only be because of a model structure. Then what we did was we compared it with a machine learning model. And machine learning model, the hypothesis here is that the machine learning model is agnostic of the functional relations between input variables and the output. We are not a priori defining a relation, right? Machine learning is just learning from the data, whatever the best relation it can find. So when we compare the results of a machine learning model with these physics-based models, after they have been fully calibrated, the difference in this will indicate what is the extent of model structural error inherent in the physics-based model. Now, in order to parse out some more that where the errors could be in plant hydraulic model, what we also did was we ran two different versions of plant hydraulic model. One where the traditional full physics-based plant hydraulic model. In the second one, we said, well, maybe the relation that some a priori relations, such as how the plant conductance varies based on psi, right, in the plant. Generally, it uses some kind of exponential relation or 1 plus psi over psi 50 to the power beta. But we are assuming that this is what the relation is generally. but we don't know if that's correct. So then what we said, okay, we'll keep rest of the physics-based model structure to be identical to what we have. But we will just assume, we will just model this G1 function based on the data, right? So other parts of the model remain the same. And if that shows a difference, that indicates that the relation of G1 as a function of theta and VPD, that is incorrect. These a priori defined relations that we use on our model, that maybe is not representative. Okay, so what do we find from this experiment? So here are our results. Let's just focus on the left panel first. So we have, I'm showing you the R square. So these are model ET versus observed ET. On the x-axis, we have empirical model, plant hydraulic model, which is explicit, means this is the standard plant hydraulic model that is represented in most physics-based model or earth system models or land surface models. Plant hydraulic implicit is what is learning from the data, and it's learning the relation of G1 as a function of theta and VPD, and then a fully machine learning model, a full machine learning. So what do we see here is that the machine learning model, first of all, it outperforms others. Plant hydraulic models is better than empirical, which we showed in the previous study as well. And implicit plant hydraulic model, which is learning the relation of conductance, plant conductance as a function of theta and VPD from the data, that is better, which means that plant hydraulic model can be improved if we, instead of using the a priori defined relation, we use a new relation, right? So it highlights that. And the same can be said even when we look at the RMSE. Now, one can argue that, well, in machine learning model, if we use more data than any of these models, like empirical and explicit model, of course, you will get better result, right? So for that, what we did, and indeed, we first used all the data that was available at eddy covariance site. So then what we did is we also did simulations by using only the data that is available, that is used by empirical model, and then only the data that is used by plant hydraulics model. And when we do that, so that is shown in case 2 and case 3. So case 1 is what we have right now, and case 2 is when we use the data which is used by plant hydraulics, and case 3 is when we use the data that is in empirical. And what we see is that the accuracy is not affected because of that. In short, what it is highlighting is that plant hydraulics model and machine and empirical model, both of them still have significant structural errors, right? There is a need to improve them. Even the plant hydraulics model can be improved. Now, there could be many errors, and it is difficult for us to parse out all the errors that are there. But we were able to parse out that, well, if you change the G1 relation, which depends on theta and VPD, if you change that and just learn it from the data, there will be an improvement as well. So certainly that is our next goal, is to improve those relations. And if we look at the results, across different land cover types. So here I'm showing you, let's say, plant hydraulics, empirical model, implicit plant hydraulics, and machine learning. So machine learning always outperformed irrespective of the plant functional types we are dealing with. And not only that, here I show that this heat map shows a functional relation between VPD on the y-axis, soil moisture on the x-axis, and the pixels represent, so the pixels here are representing the conductance, let's say. So observed conductance is this. So this is what the observed relation. And if we look at all of these 4 models, you can easily see that the machine learning model is capturing the functional dependence as well, which means it's not just have better predictability, but it's capturing for the right reasons. So the relation between VPD and conductance and soil moisture and conductance, that's represented more accurately in the machine learning model versus let's say, empirical model or applied. And that highlights perhaps the advantages of machine learning model. Now, I'm not asserting here that we need to throw away, so to say, physics-based model and move on to machine learning model. There are a lot of challenges that have been outlined in the literature already in terms of how do you scale up, or first is transferability. How do you transfer it from the site to another ungauged locations? Then the question is how well it will work as the regime changes from when it was trained. Let's say it was trained for a certain data. Now the regime is changing. How well will it work, right? And those remain open questions. And that's also a different question to answer. Should we shift and how applicable it is? But here, the point we wanted to explore is, are there structural limitations in the current models? And where are these structural limitations? And that gives us pointers. What are the processes we can improve in them? Okay, and so when we look at this, the functional dependence, we can look at it from an information theory perspective also. And so this is called functional predictability metric, and a value of 0 means that our model is representing the truth, the functional dependence. A value above 0 means it's oversensitive, and below 0 means undersensitive. And what it shows us that machine learning model captures the relation well. Plant hydraulics implicit model is much better. But one other interesting result this shows is, even though the previous project that I was showing earlier, that how the empirical model is not able to capture the sensitivity or the restriction of soil moisture or restriction of VPD value. What this is showing is, but there we cannot consider that to be truth, like plant hydraulic model result to be true. Here it shows that even the plant hydraulic model, so while the empirical model is more sensitive to soil moisture, plant hydraulic model is less sensitive to moisture. So plant hydraulic model was not the truth in that study, even though when we conducted that study, we assumed that plant hydraulic model was better. But what we are finding out in our next studies is certainly it's better in terms of predictability, in terms of representation, but it still has errors within it. And in fact, the sensitivity to soil moisture and VPD are not being accurately captured in plant. So kind of like we learn something new every day kind of situation, even though that paper also got published in a good journal, but now we are learning that, well, some of the inferences that we are drawing from that paper were perhaps, perhaps not correct, or fully correct, rather, I should say. Okay, so these two projects, so to say, highlight some of the challenges associated with predicting ET that still is there. Now let's look at, and these challenges will translate to when we want to predict stress, right? Because when we are trying to, let's say, predict stress, one of the indices which is often used, and especially in flash drought literature, in remote sensing literature, is evaporative stress index. And this is the ratio of ET over PET. And so the idea is that if there is less moisture, the ET will be smaller than PET, right? So if there is more stress, and at the extreme, let's say if ET is 0, but PET is a large value, that means the plant is more stressed, right? So ESI close to 0, a plant is more stressed. ESI close to 1, that means it's less stressed because there's enough moisture, so plant can, the evapotranspiration will be closer to potential evapotranspiration, right? Now, this formula, just looking at this formula, this shows that, well, if there are errors in ET, which is what I was showing in the previous slides, our stress index will also be incorrect, right? So that's there. But in addition to this, there are other gaps in ESI estimates or stress estimates based on ESI index. And one is, if we look at the ESI, let's say, which is ET or PT, actually, this is not giving us the plant stress. So it is giving us an ecosystem stress in some ways, because if we divide it into ET into ENT, evaporation and transpiration, and also PET into how much the PET is from the soil versus how much is from the vegetation. So actual stress that the vegetation feels is not ET over PET, which is often used, but rather T over PET of vegetation. And PET of vegetation can be different than PET from the soil, actually, right? Because the vegetation has its own conductance, soil has a different conductance, right? So the potential rate at which water can evaporate from a soil and a vegetation, or let's say a pine and a juniper, that will be very different. Right? So if we want to obtain a stress, let's say in the same area between ponderosa and pinion, the potential ET will be different. So we have to account for that before we can calculate what the actual stress is. Now, part of the reason we still continue to use it is because partitioning of ENT is very difficult, right? And earlier also I showed you that how at global scale, the range of those partitions vary from maybe 44% to 90% across different studies. And even at, a footprint scale, these partitions are not easy. Several studies have shown, like recent studies by Nharaz Zan and Eli Guzaid at Princeton, where they compared different partitioning methods and showed that there is a significant degree of discrepancy. And there are at least 20 papers on the topic exploring the differences between partitioning methods. But anyhow, the point here is this is what the actual stress index for a plant. So question is, whatever we are evaluating till now, is it possible that, or how different they are? How different is our current stress index versus what a plant experiences, right? And so to do this, again, we went to the eddy covariance sites, the crucial part, and we applied a Shuttleworth-Wallace model, which allows you to partition transpiration and evaporation. We had to account for some ecosystem conductance terms and such. If there is an interest, I can talk about that, or I can provide the references for these. But essentially, we did this partitioning using Shuttleworth-Wallace model at around 69 eddy covariance sites. And we just explored how different are these stresses based on ESI versus ESI of the vegetation, which is T over PET of that vegetation. And when we did that, what we find out is, so let me try to explain this heat map. On the x-axis is the vapor pressure deficit. On the y-axis are the soil moisture quantiles. So as I go from left to right, there is more vapor pressure deficit, or its atmosphere is drier. If I go from bottom to top, so bottom represents very moist conditions. So very moist conditions here in terms of the soil, and very dry conditions here in terms of the atmosphere. So this quadrant or this corner is in a way representing very dry conditions, both from soil moisture perspective and VPD perspective. Okay. So this is very dry conditions. This is wet conditions. So less vapor pressure deficit and well, this is actually wet conditions, less vapor pressure deficit and more soil moisture. Now, so here what we see is, and so redder it is, or hotter colors we have, that represents the difference between ESI and ESIB, which means ESI is larger than ESIB. Okay. What this highlights is, in most of the situations, it's actually hotter colors, and it indicates that ESI values are higher than ESIB values. In other words, the stress that we are estimating right now, so is lesser. So we are estimating less than the plants actually feel, right? Because larger is the ESI value, less is the stress, right? So if ESI is larger, than ESIB, that means that the stress is smaller than ESIB. So, and if we look at these different quadrants, what we can see, let's say ESI is always higher than ESIB. And if ESI is higher, that means it's we are predicting less stress than there is. So plants are actually experiencing more stress than the ESI index tells. So this is another challenge which needs to be addressed. And addressing this challenge is not easy in some ways because the partition of ENT everywhere, at ungauged locations, especially, that's quite difficult to be able to do that with high fidelity. And that is something worth exploring. So, especially for PhD students, these can be your PhD topics or proposals which you can work on. Okay, so last topic I'll maybe explore today is about challenges with mortality of the forest. So we talked about challenges with forest functions in terms of specifically ET prediction, then challenges with stress prediction. Now let's look into challenges with mortality prediction. And there was this I think landmark paper by Bill Hendrick where they mapped out the different places where forest mortality has been reported. And over time, it was, one could see that, well, most or much of the mortality happens during or after drought period. So there is a direct relation in that, and plant physiologists have studied different mechanisms that lead to forest mortality. And so we thought of coming up with a quantitative matrix that can capture the forest mortality or how, and can we predict it or not. Now, there are many different ways and mechanisms also that lead to, or there are numerous mechanisms leading to forest mortality. And the primary mechanisms, or some of the most common that have been studied or have been recognized as well, are hydraulic failure. And so hydraulic failure happens when the water potential is very less. So if we have to think of it in simple terms, let's say we have a tree, and when the tree transpires or the tree wants to assimilate carbon dioxide to prepare its food. So it opens the stomata, gets carbon dioxide, and that's how, participates in photosynthesis. The sugars get created, and that sugar goes everywhere, and that's what drives the, powers the cells. Now, when it opens the stomata, however, because of the vapor gradient, the vapor escapes, and that's what we call as transpiration, right? Now you consider a situation where, let's say, the ground is very dry, okay? And maybe the air is hot, so there is high vapor pressure deficit. So whatever the moisture is in the stomata, that will escape because you have the energy that is coming in, radiative plus sensible energy. That hydrogen bond breaks, or the moisture water molecule escapes. As a result of it, that creates a tension. Okay? Because the water molecules are connected to each other, so because of cohesion tension that acts, that leads to large negative pressure in the xylem. Now, if this pressure, because there's this negative pressure, then the root extracts water from the soil. So, and so that's what the cycle continues. But what if the water does not, there is not much of water in the soil? In that case, the water gets lost, and that is creating a large negative pressure, but there is no water to fill in. So now you have a very small plant water potential. So at those times, what can happen is, as the plant is stressed, if there is, let's say, the air gets in, and air can get in for all sorts of reasons, scientists drilling in the trees, right? Or, woodpecker, or maybe because of the infestation, any of these reasons, because there's a negative pressure, now the water, the air can get in, air bubbles can get in, and that can cause embolism, just like it can happen in our veins, right? So when that happens, there is the conductance of the xylem that reduces significantly. As a result of which, even when situations become favorable, but the conductance have been impaired, and if that impairment has proliferated within the plant, that can lead to hydraulic failure, or the plant can die, right? Because similarly, in carbon starvation, what will happen is the stomata, let's say stomata opens up, as we were talking about earlier. And in this case, in some plants, what happens is they follow what is called the isohydric strategy. So they are not as flexible in changing the plant water potential, or having that large of a negative gradient. So what they do is, when there is a loss of moisture, and they are like, well, I cannot reduce the plant water potential much, so it's better for me to close the stomata, because otherwise there will be desiccation. So they will close the stomata, but once they close the stomata, now they cannot eat. If they cannot eat, so depending on how much the carbon store is available and how much they can assimilate, if that's less than, or if they cannot assimilate as much than what is required, then carbon starvation. And now many of the times, like hydraulic failure will happen together with maybe phloem transport limitation. There has been a lot of studies, especially Gabby Catul at Duke has been studying the phloem transport and what causes this limitation. But many a times these happen hand in hand when there is a moisture deficit and in the atmosphere or in the subsurface. So we try to first come up with a matrix of mortality risk. And the way we quantified is, we counted the frequency of times psi of a plant gets smaller than psi 50. And psi 50 is nothing but, the potential at which the conductance reduces to 50% of its maximum. And that's, so to say, a plant trait we are talking. So we obtain the probability of either psi getting smaller than psi 50 or stomata closing, which is the stomatal closure. And when you evaluate it, so you put it within a soil plant atmosphere continuum model, connect the soil model with a xylem, the transport of water through the xylem, and then you connect it to stomatal optimization theory to calculate ET. And this is how the plant hydraulics works. We applied it across 13 biomes across the world. And so what we found out is, let's say here, I'm showing you the plant mortality risk in the contour lines. So one represents 1% risk of plant mortality, and this represents 40% risk of plant mortality during the time period we are considering. This is the historical data for a given biome. And as the temperature increases, then the mortality risk increases. And that makes sense, because as the temperature is increasing, vapor pressure deficit becomes higher, ET rate is higher, and as a result of which there will be more stress, and so the chance of mortality will be high. Now, however, if you look at future conditions, the carbon dioxide concentration is also increasing, which means that the stomata needs to be opened up only a little bit to be able to get the same amount of food, right? So in these cases, assuming no plasticity or adaptation of the stomata, you can think of it as that, well, as we go to higher carbon dioxide concentration, kind of similar concept as carbon fertilization, the risk is reducing. So here it's 15 and then here it's 10, right? So the risk is reducing. So if we consider all the effects together, like the changes in precipitation and temperature and specific humidity and carbon dioxide concentrations, so what we find out in these cases, there can be non-linear responses. Temperature will increase the risk, precipitation, so precipitation should reduce the risk if the precipitation increases. So sorry, I should correct it. Increasing carbon dioxide, that should reduce the risk. And then humidity, increasing humidity should reduce the risk as well. So here was one of our simulations that we conducted this was for a evergreen needle leaf biome. And what we noticed is if we only consider the risk because of changes in precipitation and temperature, yes, certainly the mortality risk would increase. But when we also, and this is what a lot of people had talked about, so the idea was that, well, droughts are causing forest mortality, and if the droughts are going to become more intense or more frequent, as a result of which maybe tree mortality will also, the risk of that should increase, right? But what we find out here is that if we consider simultaneous changes in specific humidity and carbon dioxide concentration, the risk will be much lesser than what if we only consider changes in precipitation temperature. Not only that, there are certain biomes where the risk will actually reduce. And in fact, that was the case for southeastern US as well, where the risk will be lower than what it is currently. And in fact, this idea, and as a tangential note, so to say, this idea that with changing climate, the droughts are going to become more intense and frequent, that also is debatable. You may recall there was a paper by Aijun Dai where he talked about, I think it was one of Nature journals, where he talked about, okay, droughts are becoming more frequent or more intense, something along those lines. And then Justin Sheffield has a paper where he showed, no, it's not changing at all. And then they tried to reconcile both of these papers. And the idea was, depending on the time period that you consider, you may get different results. And it's also dependent on the drought metric that you choose. And you all must be knowing, I mean, the limitations with current drought matrix. Question is how well they are represented. And lastly, one has to also look into the drought trends in the period that is of importance to you. So I recently, one of our students looked at the drought trends in the crops during the growing season in US. And to my recollection, between 50 to 60% of the area only where the drought risks were increasing. And so, you know, it's interesting. Many times we review papers and it starts with droughts are getting more intense than this. And one has to ask, really, where? Or in what sense you're talking about? And that is important to recognize. Anyway, coming back to this, what I wanted to highlight is there are multiple drivers, mechanisms of forest mortality. And then there are multiple variables that are changing. And the responses of mortality risk are very complex, depending on how these different variables are changing, is dependent also on plant functional types, whether it's evergreen needle leaf, which are anisohydric, generally anisohydric, not always. You know, it's a spectrum. Similarly, deciduous broadleaves, which are isohydric, and that also determines not only the mechanism through which plant mortality may occur, but also the risk associated with it. And these challenges exist. You know, just before this talk, Javier and Dan and I were having this discussion about, well, I mean, is PFT based classification and parameterization, is that really representative or not, right? And those are to be solved as well in this. Okay, so I'll quickly just highlight that, you know, I mean, question is, well, here are the challenges with forest mortality risk. Can remote sensing come to the rescue, right? By just visualizing it and being able to predict in certain ways. So in this regard, what we did was we just looked at vegetation index data, like an NDVI data, and we used that data within the nonlinear dynamics concept and regarding tipping points. And the idea here is, so X star is, so to say, an equilibrium. So without getting into the mathematics, what I want to highlight is you can think of this system where you have two steady state equilibriums. And when a system is in a stable equilibrium state, which is, let's say, one of those balls, what will happen is as you provide disturbance, the system will go away from it and then come back. It will retreat back. And that's what is a characteristic of a stable equilibrium. But as the system is veering towards an unstable state, or in that case, what happens is this shifts like this, which means that if I provide an impulse or there is a disturbance, the system will go somewhere and maybe tip to an alternative state. In this situation, as it's flatter, you can imagine that the rate at which the system recovers also becomes slower. And this is what is being represented here. The idea is that when the system is about to tip, the rate of the recovery from the disturbance becomes smaller. In other words, the autocorrelation that we are looking at between time t+1 and time t, that becomes high. Now, it's not as simple because there can be sometimes correlation passed on by the forcings itself, and one has to have to isolate how much of that is from the forcings and how much is from the system. And those are the things we did it in our study. But long story short, we put this idea within a dynamic linear model, and then there we looked at theta. So when there's a high, looked at how the correlation of that is changing. And then based on that, what we are able to do is we were able to identify the periods when there will be a mortality. And not only that, based on this, you can come up with an early warning signal of tree mortality. So here, for example, the tree mortality happened almost, so in this 2012, so, maybe almost 2 years before actually the mortality happened, we were able to identify the mortality just based on the autocorrelation of theta, because the trees, the NDVI has the resilience of that has reduced, or the rate of the recovery of the NDVI from its equilibrium that has reduced. So based on that, yes, we are able to predict by using this remote sensing kind of method, but it has its own drawbacks, because you cannot use it to do scenario analysis or run the what if scenarios and so on and so forth. But certainly has some potential because it does not require as much information about the plant property, but you can just gauge it and understand or quantify where there is impending forest mortality. Okay. And then we did that for a range of different species, and we found out that from 6 to 19 months lead time, one is able to do the mortality risk prediction. So I'll stop here, but what I want to conclude from this talk essentially is that there still remains significant limitations in prediction of ET, in prediction of the stress, in prediction of mortality, and some of the work that I showed that highlights that if we combine physics-based models with the data analytics and some machine learning algorithms, there could be a way of identifying where the problems are and how we could improve them. But at least these limitations will keep us busy for quite some time. So that's the good news. Okay, thank you. I'll stop.
Okay, got any questions?
Yes.
Do you talk about your decision to sort of use the machine learning to improve your mechanistic models instead of just going with the machine learning model because it predicted more accurately?
Right. So first is I should acknowledge that our purpose of the, our exploration was different, where we wanted to explore, are there errors in the current generation models? But now, if the question is, well, given this result, should we just go and use machine learning model everywhere? And that's where I highlighted that further exploration is needed to say it definitively. Certainly, it is showing a lot of potential. But that there also, there was a paper by Pierre Gentine's group where they showed a physics-based machine learning technique, not just, They showed that the ET estimates from physics-based machine learning was better during high stress or extreme periods than just the machine learning. And so my recollection, what they did was they still had some kind of a Penman-Monteith model, and they constrained the energy balance. So they made sure that the radiation and sensible heat flux and evapotranspiration that gets constrained or follows the mass balance. And when they did that, they were able to predict it better. There are parallels in other community as well. For example, in stream flow modeling also. There were papers by Kratzert et al., Freddy Kratzert and Greniering et al., where they suddenly showed that machine learning based predictions are outperforming most conceptual models. But then recently, Shen et al. Have shown that if they use the machine learning to only obtain the parameters, but still these are physics-based model parameters, then these models can even outperform the machine learning models, especially during high extreme scenarios. And part of the reason it outperforms during high extreme scenarios is machine learning, by definition, when we say extremes, these happen less often. So when we train our machine learning models, they do not get trained as well for those extreme scenarios. And so when we, however, put them within a physics-based context, where let's say the mass balance is ensured. So even when you have a 500 return period precipitation event, which was not there in the training period, because of the mass balance, the physics-based model has to produce a large stream flow. Okay? And with the parameters that get trained, then it gives a better result than just the machine. So what we are finding out is definitely during the extremes, machine learning is very useful, but people are showing that machine learning plus physics-based model is perhaps going to outperform. In other words, physics-based model still will have the relevance. In addition to that, we can talk about how well these machine learning models will perform under climate change context, how transferable they are, and finally, are they just a black box, or how much information can we derive from it, and how much understanding can we derive, right? So all of those certainly still remain an open question.
So mine's kind of a two-part question with this machine learning. By what you're saying, there are some limitations with that.
Yes.
Is there a view of maybe taking machine learning models and other models and combining them to make a hybrid model?
Right. So and that's exactly the point. When I said physics-based machine learning, they are hybrid. And now there are different terms in the literature: physics-guided machine learning, physics-aided machine learning, hybrid models. But yeah, so that's what there are studies coming up that are showing that, especially during extremes, they are very useful. Overall, they improve the predictability. Yes.
Talk about the mortality response to different climate factors. I know you touched on this a bit, but could you talk a little bit more about how your model incorporated not only the overall trend in annual precipitation, for example, but those temporal variations and when that precipitation occurs? Because obviously that has an impact on.
Right. So the model we talked about, we called it SPAT model, which is soil plant atmospheric continuum model. It's a temporally explicit model. So we ran it at hourly scale. So certainly it incorporates the precipitation temporality and such. And in the paper, we did study that how the seasonality of the precipitation plays a role in mortality. So we use this and there also we studied the role of seasonality in, let's say, Mediterranean systems versus in humid systems like southeastern US, wherein the precipitation is throughout the year. So certainly all of that plays a role. I mean, in simple terms, we can see that if less precipitation gets combined with more drier atmosphere, the risk of mortality will be higher. But many a times, mortality happens when it's sustained. And I did not put a lot of emphasis on this plot, but as you can see here, on the y-axis is the PDSI, which is the index for Palmer Drought Severity Index, so index for drought. There was a big drought here in California from 06 to 010, let's say, but not much of mortality. But after the second drought, that's when the mortality, shot up significantly. And so part of it is one, when we are talking about the drought, there also how we are calculating the drought. Is it yearly drought? Is it possible in the first period the drought was not as hotter than in the second period? Because if the drought is much hotter, then now we are talking about higher vapor pressure deficit with low storm watch, right? But the PDSI, then the second aspect is that, the frequency of it, so as with time, the situations or the conditions that prevailed during this period were such that, the frequency of either hydraulic failure or stomatic goes up. So in short, yes, the temporality of these variables play a big role. The covariation of moisture and vapor pressure deficit, that plays a big role. And that's why it's important to get a better handle of this based on physics-based model. Because let's say currently, there is a correlation between atmospheric dryness and soil moisture. A lot of studies have shown it, maybe not at daily scale, but as you go to coarser and coarser time scale, there is a high degree of correlation. Because when it's dry, when it's not precipitating, then that's when the air is also dry, right? So not a big deal. But with warming, we know that vapor pressure deficit is going to be high because of higher temperature, but the precipitation predictions are variable. Some places it's increasing and some places it's reducing, which means that the current correlations that exist in the past may not be true in the future. And so that's where another example of, let's say, a machine learning model may not work in those kind of situations. Yes.
So I know that in one of the earlier studies, you mentioned that you looked at different ecosystems in different regions. For the remote sensing study, was that across different regions as well?
Remote sensing of.
When you were
ESI?
looking at the predictive ability for the mortality?
Oh, yes. Yeah, because of lack of time, I removed it.
Okay.
But we did the spatially explicit analysis as well, where we looked at based on different species data which was there, and we looked at how the risk of that mortality is different.
Okay, yeah, I was wondering
Yes.
if in different regions, if you saw if you got the, what did you say, early warning signs?
Yes.
If you got that at different times across different regions, like if certain
Yes.
forests give you earlier signs than others.
Yeah, so that was also different, which is being in some ways shown as exceedance probability here. So there is a difference between these as well, like,
Okay.
these different species. But I recall also the extent of mortality that actually occurred, that becomes different. So for the same mortality risk, the actual mortality that happens may be different in different kind of plants. So yeah, that's definitely in the paper. I do not have the slide with me right now.
No, I appreciate it. Thank
So,
you.
yes.
Anything else? Can I ask one question?
Yes.
So, I was interested in your, environmental stress index where you tried to separate evaporation from transpiration. In my world as a soil scientist, we think that soil evaporation is pretty low. So I would think even though you separate them, that the lion's share of it, I guess, is that 80 to 90% number. It seems like your suggestion that the systems are more stressed than we're predicting them to be. Right, suggests the PET number is not changing that much, it's really more like that evaporation or transpiration. So are you does your data suggest that soil evaporation is a bigger number than we think it is?
So
Overestimating that?
certainly when we say 80 to 90%, yeah, that's not always true, for sure, and it changes during the season as well. And our analysis was not just for forested systems, so it was across all different land cover types. So it is, so I'm not sure what the number is for, let's say, pines here. But we have studied in, let's say, cropland settings where you can see T over ET, even though on an average it is 45%. T over ET over the year, and it may vary from 10% to 80% during the growing season. So during the growing season, when it's at the peak, T over ET is much higher, but in the non-growing season, it's low.
Okay, so when you incorporated a lot of places that might have a lot more exposed soil. My eastern
Yes.
seaboard bias of
Yes.
the US,
Right.
I think like soil evaporation is a quite small number. When you take out west Ponderosa Pine or any kind of arid system. Okay, that's really quite a different story.
Yes, yes, I would say that, yeah, you're right. I mean, so if the dense forest, which we see here, I would say certainly T would dominate significantly. I don't have the number between them right now.
And the stress estimates might be a little bit better in kind of
Yes.
close forest.
Yes,
systems
so in
unless-
those cases, yes.
Yeah, got it. Okay, thanks. Okay, any other thoughts, questions? Okay, so I'm gonna thank you all one more time for coming, and if you thank Dr. Kumar one more time. Get an A? Okay, Marcus.
Wider thing? They're talking about.